All right, so finishing chapter 2 with the last of the three sections, solar system models. All right, so what have we been talking about in chapter 2 so far? Celestial sphere, mostly, right? We've been talking about motion through the celestial sphere as well. And that became important when we talked about the sun, the planets, and the moon. And we introduced the idea of the ecliptic. Okay? So sticking with that notion of motion, that is the motion of the planets in particular, we want to then think about what could we learn from the motion of the planets and the motion of the sun, right? Of course, it's apparent path through the celestial sphere, known as the ecliptic. Well, those types of thoughts of thinking about that there are these special objects in the sky, the sun being, very noticeably different than stars, planets basically looking like stars to the naked eye. Really, they really don't look any different, but they definitely move differently. Stars remain motionless relative to each other. The planets don't. They're wandering stars. That's kind of historically what they were called. Well, thinkers, philosophers, early scientists have long been trying to gain some knowledge from tracking these motions and thinking about what do they tell us. And that's what this last section is all about, is the idea of building a model of the solar system, so the motion of the planets, from observations of the night sky, which is kind of a big step, right? You're just taking observations of the little points in the sky and then trying to, extrapolate that to what the whole solar system would look like, say like from a bird's eye view, like looking down at it from above. So, to get us started on that, there's one, excuse me, there's one good thing to remember is that the planets, their motion is actually close to the ecliptic. And that's because the whole solar system is like a disk. All of the orbits are only vary a little bit from each other. So the solar system is essentially flat. And there's good physical reasons for that in terms of just like fundamental mechanics, the way that objects behave and the whole way that solar systems are made, which we'll get into actually quite a bit later in a later chapter. So if you look at the planets, you can actually kind of see them follow an arc, which is the ecliptic. And sometimes they can be directly next to the sun, although you wouldn't be able to clearly see them. Another thing about planets is that they behave in this particular way called retrograde motion. And they don't do it all the time. Quite the opposite. They only occasionally go backwards, which is retrograde. So every planet at some point throughout, either, once, not even, they're not, it doesn't happen the same time during the Earth year, but every few Earth years, or, at least once a Earth year, different planets will go into retrograde motion. And this is like what in astrology, when they talk about a planet being in retrograde and that being a special significance to that planet, which makes sense, kind of in terms of you giving significance to the personality of that planet. Then if it's going backwards, well, then it's like losing power, right? Well, in a physical sense, what's happening is that it appears to be going backwards. In other words, it normally drifts a certain direction through the celestial sphere. So over every like if you looked at it every night at the same time, that planet would appear to continue to move in the positive direction of right ascension. So it would continue to be more and more east in the local sky, right? And its location in the celestial sphere would be more and more east. And but then over a period of at most a couple of weeks, the planet will instead be west of where it was the day before. And it will continue to move west for a few days and then kind of like come to a stop and then go back in its normal east of, in other words, positive right ascension direction. And what happens is we are passing the planet or the planet is passing us. That's why we see this apparent retrograde motion because we're actually, we think about our positions in the solar system when we pass Mars, because it takes us less time to orbit the sun, Mars appears to drift backwards. But don't worry about that too much just yet, because we actually will explain it in full in I want to get it right, chapter 3, so the very next chapter. But the reason that I'm mentioning it now and the reason the slides mention it is because of its relation to solar system models, because we're still talking about that. Okay, now, on a basic level, ancient philosophers, they weren't called scientists back then. And by ancient, I mostly mean ancient Greek and Roman philosophers, that they had a good understanding actually that the Earth was a sphere, and they had good demonstrations to show that Earth was a sphere, but they didn't really kind of come to the correct conclusion about where Earth was in relation to the solar system and how orbits worked. Because even the greatest or most well remembered philosophers from these ancient times all agreed, or at least the surviving publications show that they all agreed that the sun orbited around Earth. Okay? And there's actually a couple of important reasons why they came to this conclusion. And what I'll quickly mention on that topic is that they didn't think it was reasonable that Earth could be moving, especially and especially in terms of Earth's rotation, because they thought we would notice if the planet was spinning under our feet. So they justifiably ask the question, if the Earth is spinning at a fast enough speed so that we see the sun rise and set, but it's actually not rising and setting. It's just that we're spinning while we orbit it. You know, how come we don't get flung off the planet like as a modern person would say, as a child gets flung off a merry-go-round? And there's a good reason for that. Why is that? Does anyone know why we don't get flung off the planet even though we're spinning at really great speeds? Yes, it is gravity. So, and gravity is just like much stronger than early philosophers would have suspected. So they just didn't understand what a dominant force. No, I mean, they also didn't maybe have a good understanding of what gravity was, that there was just like this attractive force between matter, because that's what gravity is. And of course, gravity was not officially defined until Newton, which we'll cover in chapter 4. So they, not having a good understanding of gravity, they weren't able to fill in these gaps in their knowledge and really kind of come to the correct conclusions. So they ended up focusing on the wrong notion, and that being that Earth was fixed in place, Earth was motionless, and everything moved around us. But you remember apparent retrograde motion? Just talking about it? Well, that ended up being a bit of a problem because how do you explain planets drifting backwards to the sky every so often if they're orbiting around us and we're fixed in place? Well, the perhaps best way, although it's definitely overcomplicated, was to say that the planets moved on things that were called epicycles. And this was the term given by the most significant of these early philosophers called Ptolemy. And this model of an Earth centric solar system, also called geocentric, and everything orbiting around Earth is named after Ptolemy. It's called the Ptolemaic model, and that he came up and wrote his findings down and his conclusions in 147 AD, and they survived until modern times, but also until we get to the 15th century, and they were replaced by kind of the beginning of the scientific revolution and someone named Copernicus, who we'll see in just a second. So, with this geocentric model, the only way to explain those apparent retrograde motions of planets was to put them on smaller circles on top of bigger circles, almost like a gear on top of a bigger gear. You can imagine this whole system being like a clockwork system of all these planets orbiting around Earth, Earth being the blue dot at the center. This actually wasn't necessary for some of the planets that didn't have easily observed retrograde motion, like Mercury and Venus, although they do have some, and wasn't necessary for the moon or the sun, which never do. All right. But everything else had, all the other planets were assumed to be put on these epicycles. And the epicycles had a certain rotation rate, which was carefully calibrated, so to speak, to match observations. So this model, although being fundamentally wrong, did make correct predictions. So it could be used to predict where a planet was, when it would go retrograde, and details such as that. So it was completely accurate in that respect, but it was based off of the false assumptions despite its accuracy. And that's not to say that it would have been accurate in everything. They weren't asking the right question, right? They didn't have a hypothesis with a test that could disprove this model. Not at this time, at least. Okay? So we have this, view of the solar system being used from the 2nd century all the way up to the 16th century, right? So 1400 years of acceptance. That's a long time. And it was, by the way, is actually spread to, to Arabia, the Arabic world, which, kind of became the center of knowledge in the 11th century, and spread down into India. Don't think it ever spread directly to China, and I actually don't know what view the Chinese had around this time, say around like, the Middle Ages in Europe. But, that's all I can say on Chinese astronomy. It actually gets covered very little in textbooks. It's a major gap. But regardless, going back to our kind of Eurocentric view of things, by the 16th century, Copernicus did challenge the Ptolemaic model, and certainly people before him had as well. He was in the right place at the right time, and also did it in a way that it was published, printed, because this is after the invention of the printing press. So his view was able to be disseminated and spread throughout Europe at this time. He was essentially Dutch, came from the part of the world that is currently Holland, although he would not have called himself Dutch because they had different names at the time.
Excuse me, Professor.
Go ahead.
Yeah, so I have to go to work soon. I don't know what time we're going to be taking the quiz, but I'm not sure if I'm going to be able to do it or not. How would I be able to do that without being missing on my grade?
Just we'll get started on it, and I thought would have already started on it. So just let me just like, well, how about we start on in 3 minutes, and it's
All
15
right.
minutes, so that'll get you out of there on time.
All right.
All right. At least, you could always just like, if you need to cut out a minute early, but that, okay. So let me just say a couple more things. All right. So this is the final summary. So we got the Ptolemaic model explains planetary motion in the sky. So did the Copernican model, which had the sun at the center. Okay. The difference was that Copernicus predicted different phases of Venus. That's a testable hypothesis. And this all coincided with the invention of the telescope, so they're able to show that there was different phases. All right. Also calculated very different distances, which would then set the groundwork for Kepler's laws, which we'll talk about in chapter 4, which are these really key laws, along with Newton's laws, for understanding the physics of planetary motion. All right? It was a simpler model. It didn't require epicycles, no circles on top of circles. Okay? So, timeline here, Ptolemy, right? 2nd century AD up to the 15th century, big gap. But then comes Nicholas Copernicus, publishes his work at the end of his life. The very next generation, we have Galileo, right? Galileo Galilei. We'll talk about him in chapter 3, right? Famous for kind of being an early astronomer. And Galileo didn't invent telescopes, but he was using telescopes that had recently been invented because it coincided with his lifespan. Okay, here are the phases of Venus, which confirmed the Copernican model, and Galileo helped confirm that model. All right, so we found out that the Ptolemaic model was wrong by following the scientific method. All right, that's it. Let's stop that recording.